Hello, everyone. So my name is Baptiste, and I'm going to present our MLDM M2 MLDM project, partial differential equation discovery from unregistered images. So first, as François said, I'm going to do a general introduction of our project. So what we are interested in here is partial differential equation discovery. So what is a PDE, so partial differential equation? It's some equation that describes some physical interactions, such as the ones that can appear at the interface between a laser and some surface, such as a metal plate. And at this interface between both, there is some self-organization that appears with some patterns that are being shaped on the matter at the nanoscale level. So what is a PDE? As I said, it's an equation that describes some physical interactions. And here we can see the patterns evolving with the number of pulses of the laser, so evolving with time. And this evolution of patterns can actually be described by an equation that says that the temporal derivative is a linear combination of the spatial derivatives. An example of a PDE is, for example, the Kuramoto-Sivashinsky PDE, which we will use in our artificial data. So the motivation behind doing PDE discovery is that each resulting patterns that can be formed by different laser parameters can have different specific properties, so that can be useful, for example, in some industrial applications. And these patterns, as I said, are also governed by an underlying PDE, which is most of the time unknown. And the goal of PDE discovery is to infer this PDE directly from the data, so directly from the patterns evolution. And then later on, we could, for example, establish a relation between this governing PDE and the laser parameters in order to discover new patterns. So some related work and existing methods for PDE discovery is, for example, SINDI, where first you have to construct a library of spatial derivatives. And then as your time derivatives can be approximated by a linear combination of spatial derivatives and some coefficients, you can perform a regression on these coefficients in order to find them and reconstruct your PDE directly from the data. So the ideal situation to perform this PDE discovery technique would be to be able to have succession of patterns that comes exactly from the same physical location. So for example, pulsing one time at a location, taking an image for frame 1, and then after pulsing 2 times at the same location, taking frame 2, and etc., etc. However, our problem is that it's impossible to take a picture between 2 laser pulses. So the laser needs to move between images. So what we have is a sequence of patterns evolution where each frame comes from a different physical location. And this leads to our main problem, which is unregistered images. So what does it mean? It means that between an image at time t and an image at time t+1, you have unregistered pixels, which means that a pixel at time t does not correspond to the same physical location, underlying physical location from a pixel at time t+1. So you cannot compute the derivatives that are needed for classical PDE recovery methods, such as SINDI, that would expect some registered images where only the underlying matter is moving and not the whole coordinate system. So this is the end of my general introduction. And now I'm going to present our group method, which is called joint optimization of registration and dynamics. So first, how did we mimic our real data with some artificial data? So what we did is that first we used two PDEs, so Kuramoto-Siewieczynski and Swift-Hohenberg, that are PDEs that exhibits kinds of the same patterns as our real data. And then for each frame of our data set, we take this frame from a simulation that comes from a different random initial condition that mimics the fact that we are moving on our metal plate. So our group method, joint optimization, is trying to solve a joint minimization problem. So first, what we do is that we extract some patches in the frames. So here is a frame at time t, and here is the frame at time t+1. So it's the evolution of the pattern. And we extract some patches, and the idea is to try to find which patch at time t+1 corresponds to the evolution of a patch at time t. However, we have two problems. So first, we have the matching problem because we actually need this PDE, so the partial differential equation, so the coefficient xi, to predict which patch corresponds at the time, the next time step. And we also have the discovery problem because we actually need those pairs of evolution patches to apply the regression problem and to discover the coefficient xi. I will not enter into the detail of the mathematical formulation, but the idea is to search jointly for the parameters xi and the pairs of patches. So how did we implement this idea? We did it by using an alternating minimization algorithm, where first we fix the coefficients xi, so we fix the PDE, and we try to find some matches between two frames, so between time t and t+1. We find matches that are coherent with this physical equation. And then once you have those pairs, you can perform some PDE discovery methods, such as the one I talked earlier about, Cindy, and perform a regression problem to find the coefficient xi of your PDE. And you iterate until convergence of your PDE. So some results on our artificial data. So here we have an example of our data that we use. So we see that the images are unregistered, so which means that between two frames, so this is an evolution over time, between two frames, we see that the evolution of the patterns is really not smooth because it's simulating the fact that it comes from a different location on the plate. In the middle, now you can see the results when considering the evolution of the patterns at one specific location, so registered images. And now on the right, you can see the results of our method after being applied to artificial data that were unregistered. We see that we were able to discover some PDEs that were reproducing exactly the correct patterns of the true PDE. On real data from laser-matter interaction, we had worst results because probably because the images are much more noisy and the methods would require much more tuning to work. But we see that we can still capture some patterns, such as the horizontal stripes that we see here, and some dot patterns that appear also in the real data. So to conclude, we explored PDE discovery from unregistered images. We proposed a joint optimization framework in order to solve the problem. We showed that we were able to recover some known physics from known PDEs from artificial data. We then try to apply it to laser matter interaction data. And some perspectives on this work would be to first investigate how to evaluate the quality of a discovered PD when it is unknown. Then to focus on real data application, so to enhance our method, and then later on to relate the coefficient xi to laser parameters. Thank you, everyone.
Thank you very much for your presentation. So, master student from MLDM, you should have questions, of course. If you have not, you should disappear from the master MLDM. Ah, yes.
So you mentioned that the algorithm, alternating algorithm, the initialization was done like, the matching thing. So did you do that like manually or was it a random? And if is it prone to the like selection of initialization?
So you're talking about the initialization of the coefficient xi? Yeah. So we just initialized the coefficient xi to a vector of 0 at first. So the first step of matching is simply matching the pixel value. But you could imagine to, for example, add a prior on your coefficients xi. So if you have an idea of what your PDE should look like, you could add some prior information of on these coefficients in order to directly at the first step of matching, consider this prior PDE to match the patches.
Thank you.
Okay.
I have two questions. The first one is if you consider that maybe the changes in matter could be discontinuous, and in that case, could we still have a PD, a real PD that can be obtained? Yes or not?
So you're asking if so each of the frames are coming from the same PD.
From the same spot?
No, not from the same spot, but from the same underlying PD. So
okay.
with one PD, so you take a random initial condition.
Okay, but
you fix one PD, you simulate until step T, you take this frame T, and then for frame T plus 1, you do another simulation with the same PD, but a new random initial condition. And you take this frame T plus 1 and you concatenate everything.
Yeah, but my question is regarding the real images. If there is no continuous modification of the images, did you consider that could be discontinuous in real life?
So
yeah, this change.
Okay, this. So this is the problem we are trying to solve, is that it's the same. So here, the PD that dictates how a pattern evolves between the here at the interface, it's the same if you are here or here or here or here. It's just that the initial condition that the PD starts on is a little bit different at the nanoscale level, but the underlying PD forming these patterns is the same.
Okay.
So when you are here, so I don't know if it answers your question.
No, my question is, I know that the images are being modified since the laser is staying more time and in one spot or different spots, but is if this modification is continuous or not? I mean, maybe because the laser is staying more time and heat is different, or the matter is different, maybe it's not continuous. So I don't know if that was an hypothesis and Why? If
So I'm not sure I understand
maybe we can discuss
your
it
point.
later.
Yeah, maybe.
Yeah.
I encourage to discuss after the session. And thank you for this clear presentation. I was wondering if it's possible to predict something which corresponds to symmetry breaking. I mean, in your dictionary, you have some gradients, different terms based on gradients to the square, and so on. So it means that you need to have something which is already oriented along given direction. And experimentally, we observe something which sometimes breaks the symmetry. I mean, you have bifurcation, you have something which is a stripe, as you have shown at the illustration at the end. And finally, it becomes something which is hexagonal. So can it be included inside the simulation, I would say, or inside the dictionary you have, or it's difficult to include because it's not something which exists in the original images?
So here in our library, we include a lot of possible terms, but
yeah, but they are based on the image which exists at the time t. And if you have a bifurcation, it means that you could have a flow of material along a direction which was not existing before. So you don't have the ux or the second derivative of x which exists at the time t. It just starts to occur, and it becomes from the laser irradiation. It exists due to the laser radiation. It's not existing in the image.
Okay. So I don't know how to answer this question. Sorry, but yeah, it's an interesting point.
Okay, thank you. I was wondering, at the end of your talk, you were showing real images. And
real ones?
Yeah, real data, and you were saying real data are more noisy, but on the images, they are quite nice.
Yes, they are quite nice, but at the pixel level, they are much more noisy. And as we need to compute derivatives between two images, if it's noisy here we cannot see it with our eyesight, but if it's noisy at the pixel level by some observation noise.
But it seems less noisy that you are discovered images.
Yes, okay. Yes, but the resolution is not the same.
Yeah.
From the...
Okay, so thank you again for this presentation.